is Hilal. In this video, we will discuss about the Cobb Douglas production function in detail and its mathematical interpretation and its various properties. First, this Cobb Douglas production function was given by the Charles Cobb, who was a famous mathematician, and his friend that was the Paul Douglas, who was an economist, and later he became the senator from Illinois in United States. But its functional form was first proposed and used by Kunt Wicksell. Now, what is its original functional form? We write it as y is equal to a times k to the power alpha and L to the power 1 minus alpha, where alpha lies between 1 and 0. The value of alpha lies between 0 and 1, where y is the total production. This y is the total production. This A denotes the total factor productivity or the state of technology used. Here this K is the amount of capital, and this L denotes the amount of labor, that is labor, where alpha and 1 minus alpha are the factor shares of labor and capital and labor. That is, alpha is the labor share, capital share, and 1 minus alpha is the labor share. Now, the important property of this Cobb Douglas production function is that it gives us constant returns to scale. That is, the property is constant returns to scale. And we will explain it here. By constant returns to scale means if we double the inputs, that is, if we double the inputs K and L, holding A as constant, the output Y will also get doubled. That means if K and L are doubled, that our output will also get doubled. This means the constant returns to scale. Why it is? Because alpha plus 1 minus alpha is equal to 1, because this alpha and alpha will get cancelled and we get 1. That means sum of the exponents is equal to 1. Then we get the constant returns to scale. Now we will prove it how it is done. Let us say we have the production function that is f of k l is equal to, we will write this, this is a k to the power alpha and L to the power 1 minus alpha. Now, if we if we increase the K and L by a proportion, let us say if we increase K by lambda, that is, and also we increase L by lambda, that means increasing the inputs by a fixed proportion, then what will happen here? This is A, so in place of K we have now lambda K, so we will write lambda K to the power alpha, and similarly L is lambda L here, so we will write lambda L to the power 1 minus alpha. Now giving some manipulation to this will become a lambda to the power alpha k to the power alpha, because the exponent is to these both lambda and k, and we expand it, so this will become lambda to the power alpha k to the power alpha. Here we will do the same, that is lambda 1 minus alpha and l to the power 1 minus alpha, which is equal to here it is equal to, here it is alpha, sorry, lambda to the power alpha. I will write here lambda to the power alpha, and I will write this with this here. So rearranging this is 1 minus alpha, and we have k to the power alpha here, and l to the power 1 minus alpha. Now which will come out to be here, this is alpha, lambda. Since bases are same, we can add up the exponent, so this will become alpha plus 1 minus alpha k to the power alpha l to the power 1 minus alpha. Now alpha and minus alpha will get cancelled, we get lambda times 1, which is equal to lambda times k to the power alpha l to the power 1 minus alpha, which is equal to lambda times f of here it is equal to lambda times f of k l. That is, when we increased capital and labor by same proportion, our output also gets increased by the same proportion, that is by lambda. That is to say, if it was here 2 in place of 2, that is if lambda was 2, then it was 2k and 2l. That means doubling the inputs will give us here 2. That means our output would have also get doubled. So this was proof why it gives us constant returns to scale. Now if so I will write here that means, that implies f of lambda k lambda l is equal to lambda times f of k l. That means if we double the inputs, our output will also get doubled. Now if the sum of exponents, if sum of exponents, that is if sum of exponents was less than 1, that is if I will write here, if alpha plus 1 minus alpha was less than 1, then we would have the decreasing returns to scale. Similarly, if the sum of exponents was greater than 1, we would have the increasing returns to scale. So here it will give us decreasing returns to scale, and if it was alpha plus 1 minus alpha, if this very expression was greater than 1, then it would have given us the increasing returns to scale, I hope I make myself clear up to this. Now another property of the Cob Douglas production function is the diminishing marginal product of each input factor. That is, another property is diminishing marginal product marginal product of each input factor where our input factors are capital and labor. Now that means first we will see the marginal productivity of labor. Now marginal productivity of labor is given by, first, the definition of the marginal productivity of labor is increase in the output with 1 unit increase in the labor, holding the capital and the state of technology constant. That means marginal productivity of labor is, so I will write here, marginal productivity of labor is increase in output with 1 unit increase in labor, holding capital and the state of technology or total factor productivity constant. Now how is this marginal productivity of labor calculated? We have seen in the calculus classes in earlier videos on mathematical economics. Marginal productivity of labor will be simply the first derivative of this Cob Douglas production function. That is, the first derivative of the Cob Douglas production function with respect to labor will give us the marginal productivity of labor. That is, the partial derivatives of the Cob Douglas production function will give us the marginal productivity of labor. So we will calculate this, which will be equal to, that means differentiating this, so I will write here, that will be equal to dFKL divided by dL, or we could write dy divided by dl if we write this very equation. So differentiating partially this with respect to the labor first, so this will become, here a is, we have to do nothing with this a because a and k are constant. A, then we have k to the power alpha, this is also constant because of the very definition of the marginal productivity of labor. Now differentiating L to the power 1 minus alpha. Now how will it get differentiated? This 1 minus alpha will come down, it will become the coefficient, so I will write it as 1 minus alpha, and this exponent will get subtracted by 1, so this will become L to the power 1 minus alpha and subtracting it by 1. Now this is equal to, now here minus 1 and 1 will get cancelled, we will get, so I will write here, it will become a k to the power alpha 1 minus alpha, this minus 1 plus 1 will get cancelled, we will get L to the power minus alpha, or we can write it as 1 minus alpha, I have rearranged this and written it first. This is 1 minus alpha here, and I will write this k alpha and L to the power minus alpha, which will become 1 minus alpha k to the power alpha, and L to the power minus alpha will become L of alpha. So this comes out to be 1 minus alpha k divided by L whole to the power alpha, because we have the same exponents. in numerator and denominator. That means our marginal productivity of labor is equal to 1 minus alpha times K divided by L to the whole power alpha. Now this means this gives us diminishing marginal product as L increases. That means this marginal productivity of labor is decreasing in L. That means we get the diminishing marginal productivity of labor as the number of labors as L increases. But we have to wait a minute here. But if K increases here, that is if the amount of capital increases, if K increases here, then what will happen? This whole ratio will get increased because K is the denominator. If denominator increases, this whole fraction will get increased. That means the marginal productivity of labor will get increased. That is, marginal productivity of labor will increase. Okay. Now coming to the marginal productivity of capital. Similar scenario is marginal productivity of capital is equal to marginal productivity of capital is increase in output with 1 unit I will write it 1 unit increase in capital and holding output, that is holding the capital and labor and a state of technology constant. That simply means marginal productivity of capital means increase in output. How much output will get increased if we increase 1 unit of capital holding labor and state of technology or total factor productivity constant. That marginal productivity of capital is simply, as we have seen here, that will be the partial derivative of the Cob Douglas production function with respect to capital. That is, I will write here MPK is the partial derivative of production function with respect to capital. So here I have written f of KL. It is same if I write y, because y and f of KL are same terms. That means we have to partially differentiate the Cobb Douglas production function with respect to capital. Now what will happen to this now? Here A is as it is. We have to differentiate K to the power alpha. Now alpha will become coefficient. This alpha will become coefficient. So I will write here alpha K to the power alpha minus 1 and times L to the power 1 minus alpha. That is, we differentiate this very function with respect to capital. Now giving some manipulation to this, this will become, we can write it as, so I will write here to save the space. So this is alpha times A. Now K to the power alpha, I could write it as K, if I factor out minus 1, so this will become minus 1 minus alpha, because minus 1 into 1 is minus 1, minus 1 into minus alpha is plus alpha, and we have L to the power 1 minus alpha. Now we can write it as alpha A alpha A. Now K, I can write it as I will write it 1 divided by K to the power 1 minus alpha, because minus 1 will become plus 1 here in denominator, and L to the power 1 minus alpha. Because of the simple, if we have x to the power n, it will become 1 divided by x to the power minus n. This very algebraic relationship is here. 1 divided by k 1 minus alpha. This minus becomes plus. Now giving further manipulation, this will become alpha A L divided by K whole power 1 minus alpha. So this is our marginal productivity of capital. This is also that marginal productivity of capital is equal to this term is decreasing in capital. That means we get diminishing marginal productivity of capital. But if we increase the number of workers, that is, if L is increased here, if L gets increased, then our numerator gets increased, so this whole fraction will get increased. That means if we increase the number of workers, then marginal productivity of capital will increase. We can see this ratio will get increased. That means if we increase L, marginal productivity of capital will increase. But if we hold this relation, then marginal productivity of capital is diminishing. I hope I am making myself clear up to this now. Now we will see another property, that is constant income share of factors. That is given by another property is the constant. So I will use another constant. Let us take the red one. Constant income share of share of factors. What does this mean? We will see how much capital contributes on the production of output and how much capital labor contributes on production of output. Now we will see first of all labor share. Now labor share is simply the real wage, that is wage rate divided by price times number of laborers employed divided by total output. Now this W divided by P, real wage, is actually the marginal productivity of labor, that is equal to MPL times we have this L, number of laborers, divided by the total output. Now marginal productivity of labor, which we have calculated somewhere, this is the marginal productivity of labor. So we will write in place of MPL, we will write this very expression, that is 1 minus alpha K divided by L to the whole power alpha, and we have to multiply it by L and divided by the y. Our y is this a, k to the power alpha, a, k to the power alpha, and l to the power 1 minus alpha. Now evaluating this or simplifying this, this will become 1 minus alpha. This will become here k to the power alpha. This will become l to the power minus alpha, l to the power minus alpha times l divided by a, k to the power alpha, l into l to the power minus alpha. We have expanded this because it is l to the power 1 times l to the power minus alpha. Because here bases are same, but we can add the exponents. Now there will be the cancellation, the massive one. This l to the power minus alpha, l to the power minus alpha will get cancelled. K to the power alpha, k to the power alpha will get cancelled. So actually I have missed here something. Also this l will get cancelled. Somewhere I have missed something, that is this very a. It is here a, because state of technology I forget to write this. I apologize for this very mistake. So here we have this a also, a times, so this a will also get cancelled. So this a and this a will get cancelled, and we are with only 1 minus alpha. So we get 1 minus alpha. That shows the labor share of income. This 1 minus alpha shows the labor share of income. Labor share of income. It is constant. It does not depend upon the level of capital or labor. So this is a constant term. Also, it is the output elasticity of the labor. We can say it is the output elasticity of the labor. How much our output will increase when we increase the labor. So this value is constant. Coming to the capital share now. Capital share is simply the rental price of capital, which is given by R divided by P times the number of capital units used, that is K, divided by Y, that is the total output, which is equal to marginal productivity of capital times this K divided by L. Now MPK we have calculated somewhere. Here we have calculated this. Now then our MPK is, that is M. So I will write here in place of MPK we will write this very expression, that is alpha A L divided by K 1 minus alpha times this K divided by, sorry, it is here Y. Our production function is A K to the power alpha L 1 minus alpha. Now giving some manipulation here, we have alpha, we have this A. Now this will become L to the power 1 minus alpha, and this will become K to the power alpha minus 1. How? Since this is K, So I will show it later. First I will write here times k divided by a k to the power alpha l to the power 1 minus alpha. Now how this k to the this became alpha minus 1. So I will show it somewhere. Since it is here 1 divided by k to the power alpha, 1 divided by k to the 1 minus alpha, we could have written it as k to the power minus 1 minus alpha, because of the identity which I have shown you, that if we have 1 divided by x to the power minus n, this will become x to the power plus n. Since it was x to the power n positive here, then we when making it on the numerator side, this will become minus. Now this will become k to the power minus 1, and this will become plus alpha, that is alpha alpha minus 1 we get. I'm sorry if I could not explain it clearly because of the lack of space. I will show somewhere. Now this will come out to be alpha, this is a l to the power 1 minus alpha. Now k times alpha minus 1. Here the exponent is, if there is no exponent, there is 1 always. So this will become plus 1. This plus 1 minus will get cancelled, and we are with a k to the power alpha and l to the power 1 minus alpha. Here will also some terms will get cancelled, so we are with this alpha. So this alpha shows the capital share, and it obviously does not depend upon the amount of capital or labor, so it is independent of k and l. Now there was some very important concept I was going to make you clear, that is this 1 minus alpha and alpha, these are the output elasticities of this values of labor, and this is output elasticity of capital. Now what does this mean? This means percent change in the output with percent change in the this very exponent.